Quantum mechanics, the science of the very small. Subatomic particles, wave functions, entanglement, uncertainty. These aren't just abstract scientific concepts, they're psychological puzzles. Why? Because to understand quantum mechanics is to confront the limits of human intuition, perception, and even reality itself. This is the psychology of quantum mechanics. Let's begin with the mind. Human brains evolved to throw spears, not solve Schrödinger's equation. We understand cause and effect. We expect things to be either here or there, not both. But quantum mechanics? It laughs at those expectations. Schrödinger's cat paradox. Wave-particle duality. Light behaving as both a wave and a particle. Psychologically, we're wired for classical physics. Gravity, friction, object permanence. But quantum mechanics demands that we abandon our everyday logic. This cognitive dissonance between what we intuit and what experiments reveal creates what some physicists call quantum weirdness. But is it the universe that's weird, or just our brains that can't handle it? One of the most mind-bending ideas in quantum theory is the observer effect. In some interpretations, the very act of observation appears to affect the outcome of an experiment. The double-slit experiment, collapse of the wave, function upon measurement. This raises a psychological question. What does it mean to observe something? Does consciousness play a role in shaping reality? Some interpretations, like the von Neumann-Wigner interpretation, suggest the observer's mind collapses the wave function. Others reject this as solipsism dressed as science. Still, the fact that this debate even exists reveals something important. Our understanding of quantum mechanics is as much a philosophical and psychological struggle as it is a scientific one. Consider the EPR paradox. Two particles become entangled, and measuring one seems to instantaneously affect the other, no matter the distance. Einstein called this spooky action at a distance. This goes against our basic psychological models of locality, how things should only affect their immediate surroundings. The discomfort we feel when confronting these paradoxes is a kind of cognitive dissonance, two conflicting ideas in our minds fighting for dominance. Our brains resist the implications of non-locality because they conflict with everything we've learned through sensory experience. Because quantum mechanics doesn't offer a single, clear-cut interpretation, we're left with multiple narratives, each psychologically satisfying in different ways. Copenhagen interpretation, collapsing wave functions. Many worlds interpretation, infinite realities, Bohmian mechanics, hidden variables. Each interpretation appeals to different psychological needs. Some prefer the elegance of mathematical determinism. Others are more comfortable with randomness. Some cling to locality, others embrace the vastness of the multiverse. In the absence of definitive experimental evidence, the debate becomes psychological, a matter of preference, belief, faith. Interestingly, some psychologists and cognitive scientists are now borrowing ideas from quantum mechanics, not to explain particles, but to understand the mind. Quantum cognition, using quantum probability to model decision-making superposition of mental states, holding multiple contradictory beliefs. Interference effects in memory and thought. This doesn't mean our brains are literally quantum computers, but the mathematics of quantum theory, uncertainty, entanglement, superposition, can sometimes model the messiness of human thought better than classical logic can. Quantum mechanics has also become a psychological Rorschach test. From pseudoscience to New Age mysticism, people project their desires, beliefs, and philosophies onto it. Quantum healing misinterpretations in pop culture, the misuse of entanglement or energy in non-scientific contexts. Why is quantum mechanics so often misunderstood or misused? Because it's mysterious. And mystery invites projection. People seek meaning where science offers only probability. The psychology of quantum mechanics also affects education. How do we teach what can't be visualized? What does it mean to truly understand quantum phenomena when every analogy breaks down? Feynman's quote, "If you think you understand quantum mechanics, you don't." Use of metaphors, waves on a pond, coin flips, etc. To teach quantum mechanics effectively, educators must confront not just the math, but the psychological resistance students face when their intuitions fail. Quantum mechanics is not just a theory about particles and forces. It's a mirror held up to the human mind, a reminder that the universe is not obligated to make sense to us. And yet somehow, we persist in trying to understand it. In the end, the psychology of quantum mechanics reveals something humbling: the limits of human understanding and the infinite curiosity that pushes us beyond them. The universe may be quantum, but our struggle to understand it, that's deeply human.